Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, we were discussing this chemistry of 3D elements in which we have started the discussion of crystal field theory in case of the coordination complexes. We have seen what is crystal field theory, and now we are applying this theory to various types of arrangements or geometries such as octahedral, tetrahedral, square planar, etc. We have last time discussed the octahedral crystal field theory and CFT also. Today we will discuss this Jahn-Teller distortion. Normally, in case of octahedral complexes, we are expecting that the ligands are arranged in the direction of x, y and z axis, as a result of which we get the geometrical arrangement called octahedral structure. But sometimes some factors makes the octahedral arrangement distorted to some extent, and it depends upon various factors. That is, it depends upon the electronic configuration or the number of electrons present in various d orbitals of metal ion. So this is discussed here in Jahn-Teller distortion. If you consider these configurations, that is D9 configuration and D4 configuration, in which it is high spin complex. So in these complexes, that is octahedral complexes, we find this distortion. This distortion is observed. For example, CuF2 in solid state shows the distortion around the metal ion, which contains the copper at the center. Similarly, in case of CrH2O6, 3 plus or 2 plus, 2 plus. It also shows the octahedral arrangement, but distorted octahedral structure. Now we will see the general arrangements or generalization of the arrangement of these structures. We know that the metal ion is at the center and ligands are arranged in this way. This is oxidation state, say N plus. Now, if we compare, say these bond lines shown in blue color are A or E, whatever it may be. So each bond distance is A and this is E. So these are E bond distances. Now here you will find that in this case we observe that this A is smaller than E, A is smaller than E. Then if you consider another structure in which metal ion is so here this A and E. So you will find that here A is longer than E. A is longer than E. So here you will find that the complex is elongated in the direction of z-axis. Complex is elongated in the z direction, in the direction of z-axis. Here the complex is compressed in the direction of z-axis. That is why the ML A distance is greater than E. So the two ligands are coming closer and which are present in the direction of z-axis. Here these four ligands are coming closer while these two ligands in the direction of z-axis are moving away. So these are two situations in which we can find the distortion. We can have different examples. So first of all we will see the D4 high spin complex. D4 high spin complex. Now here we find that in case of this D4 complex, so this is D4 complex. What happens? The distribution can be shown in this way. So these are 3D orbitals. So they are split into this is isolated metal ion. This is spherical field. These are T2 orbitals, that is dxy, dyz, and dzx. And these orbitals this is dz2 and this is dx2 minus y2. Now, in in case of this D4 configuration, the electron distribution is like this. Out of 4, 3 electrons will enter into this T2G. Now, the 4th electron will go into these EG orbitals. These two are called EG orbitals. But here dz2 is this initially the dz2 and dx2 minus y2 are degenerate. But since there is only one electron available for distribution, it can enter into this dz2 orbital. It can go into this dz2 orbital, which is lower in energy. If this is lower in energy, then electron may also enter into this orbital. But out of these two, the dz2 becomes lower energy. So that electron, 4th electron enters into this dz2 orbital. Now, as a result of this, these 3 orbitals are lying between x, y and z axis. So you can consider this as x axis, this as y axis, and this as z axis. So you will get this idea that these T2G orbitals of metal ion are lying between the x and y axis, x and z axis, y and z axis. So ligands which are approaching the metal ion in the direction of y axis are lying away from this orbital, metal orbital lying in the direction of y-axis. So here we will find that these x2 minus y2 orbitals are lying in the direction of y-axis and x-axis. So they show repulsion only when the metal ions have electrons in the orbitals in the direction of y-axis. So the ligand approaching to the metal ion, if faces the repulsive forces due to the electrons present in dx2 minus y2, then these orbitals, the metal ion and this length will be increased. So the repulsion will increase. But here there is no electron in dx2 minus y2. So the d orbitals lying in the direction of x and y axis, that is dx2 minus y2, will not face any repulsive force with the ligand electrons. As a result of this, the ligands are lying relatively much closer to the metal ion. But here you will find that this electron is present in dz2 orbital, and dz2 is lying in the direction of this z-axis. Ligands are also approaching in the direction of z-axis. So the electron of metal ion in the dz2 orbital will suffer strong repulsive force or repulsion with the ligand electrons. So the ligand electrons and this electron will show strong repulsion. As a result of this, these ligands are moving away from metal ion. So the ligand, this ligand, and say we can say this is one and this is two. So these two ligands are repelled away by the electron present in this dz2 orbital. So that is why this complex shows elongation in the direction of z-axis. So this complex is called elongated complex, and this is called a distortion. Means in normal octahedron all the bond lengths are same or identical, but due to the unequal distribution of electrons, there is no electron here, but this dz2 contains electron, means the distribution of electron in the EG orbitals is unequal. There is only one electron, but there are two orbitals. So one electron that will enter into Z2, and because of this, the elongation takes place in the direction of Z-axis. In this case, you will find that the orbitals which are present here will show only this portion. That is T2G orbitals. Then there are this is dZ2 and this is dx2 minus y2. So if that fourth electron goes here in dx2 minus y2, even though dZ2 is lower edge, if the electron enters into this dx2 minus y2, then what happens? The ligands which are present in the direction of x and y axis, that is dx2 minus y2, are showing repulsion with the metal ion d orbital, metal ion electrons of metal ion in the dx2 minus y2. So they will show repulsion. As a result, this metal will repel these ligands, four ligands which are present in the square plane, that is dx2 minus y2. And here dZ2 has no electron, so it will not show any repulsion along in the direction of z-axis. As a result of this, the distance ml is shorter than this E. So A is longer, or E is shorter than A. Both the things are same. So this is called the Jahn-Teller distortion. Now we will see this Jahn-Teller distortion. We have seen in this in case T4 case. Now we will see the same in other case, that is D9 configuration. So if we see this D9 configuration, we will find that the distribution is like this. This is T2G, then this is dZ2, this is dx2 minus y2. Now there are 9 electrons, so these are distributed in this way: 6, 7, 8 and 9. 6, 7, 8 and 9. So this is unequal distribution. So you will find that the electron density in this case, in the previous discussion we have seen that electron density lies more in this ml direction, in the direction of this ml. Now here you will see that the electron density is lying in the direction of in between x, y, z and zx, these T2G orbitals. So dxy, dyz, and zx. So these are electrons which are lying in between x and z, y and z, x and y. here, but these electrons are lying away from these four ligands in that is x and y axis, so they will not suffer any more interaction or repulsion with the ligands. Now here dZ2 has more electron density in the direction of z axis. So dZ2 we have 2 electrons, so there is more electron density. As a result, the metal ion electrons will repel the electrons of ligands. As a result, the elongation of this octahedron will take place. Now here in this case, D9 configuration, you will find that this is T2G. So the electron distribution is like this. So this is dZ2, this is dx2 minus y. Here electron density, these 3 electron pairs are same, that is T2G has same situation here. There is 1 electron in the direction of z axis. So the repulsion between this metal and ligands are relatively less because there is 1 electron. In the dx2 minus y2, there are 2 electrons, means electron density is more in the direction of x and y axis. As a result of this, the 4 ligands, that is L1, L2, L3 and L4, are showing stronger repulsion. As a result, these bonds, ML bonds, 4 bonds are larger, means A is larger than E. So the D9 configuration also exhibits the same kind of distortion. Now this resulting structure is called a tetragonal. This is the resulting structures are called tetragonal. So the distortion is also called a tetragonal distortion. Now this Jahn-Teller theorem shows that, or it states that, when the molecule is non-linear, or molecular system is non-linear, the degenerate orbitals undergo splitting. The degenerate orbitals undergo splitting, and this will create the instability, and that will result in the distortion in order to attain stability. So the stability of the structure is arising due to the existing destabilized structure. So the energy is given out, or the repulsions are minimized by either pulling or either moving the ligands in the z direction or in the direction of x and y axis. So depending upon the distribution of electrons among the d orbitals. This observed tetragonal means degeneracy. Here you will find that the degeneracy of these 2 orbitals is split. Here it is also splitting. So this splitting is observed only because when the electrons are unequally distributed. In this case there are 3 electrons, so 2 electrons are present in one orbital, one in other. Here it is in the reverse order. Here it is dZ2 with 1 electron, dx2 minus y2 with 2 electrons. So this is unequal distribution of electrons. So this causes the distortion. So the resulting structure is called a distorted octahedron or tetragonal distortion. So the symmetry of such structure is lowered, and because of this the energy of the system or structure is also lowered, and for this purpose the degeneracy is to be removed. the degeneracy of these two orbitals is necessarily to be removed. Then only the lowering of energy of the complex is possible. For example, the octahedral structure has initially octahedron has, that is, OH symmetry, but this structure is changing to D4H, that is, these structures. So these are called D4H structures, that is tetragonally distorted structure. So we find that the splitting of each orbitals resulting in the change of symmetry. The symmetry changes from octahedral to D4H. So these structures are symmetrically having this D4H. So they have this symmetry called the D4H, and the structures can be here represented as, so we can, for our convenience, we can represent this as A and this as structure B. So here the Z component shows repulsion, and here the Z component is away from the repulsion. So the destabilization is taking place in the direction of xy and this x2 minus y2, dxy and x2 minus y2. So this is about the distortion called Jahn-Teller distortion. So this is important type in octahedral geometry according to crystal field theory. So we will stop our discussion here. If not, please subscribe to this channel, press the like button and bell icon. So keep watching. Thank you very much.